Hi, this is Jackilo L. Kikoy, and for today's video, we will going to solve 5 problems involving center of gravity or the centroid of an object. Second is about parallel access theorem application on the moment of inertia, and next is the composite areas, and the fourth one is about finding the product of inertia, and lastly is the mass moment of inertia. Shall we now begin with our first problem on center of gravity or the centroid of an object, specifically in a parabolic spandrel, which is our main objective in this problem, where we have to locate its centroid y bar on this shaded area. So shall we now start solving? Let's go. So our first problem, we are tasked to locate the centroid y bar of this shaded area. So in this figure, it is a parabolic spandrel. This object is a parabolic spandrel, which we can see that the point somewhere in this region represents a y is equals to 1/4 x squared, and we can carry it off with some distance of x is equals to 4 feet and a height of 4 feet. The area is equals to y dx, where our y is equal to 1/4 x squared, as what we have said earlier. So which gives us 1/4 x squared dx. So our x with squiggly line is equals to our value of x. So with the formula of x bar is equals to the integral of x d area over the integral of d area. So we will now going to substitute the variables that we have identified or denote earlier, which our x squiggly line is equals to the value of x, and our d area is equals to the 1/4 x squared dx. So we're now going to substitute with its formula. So integral of x times 1/4 x squared dx over the integral of 1/4 x squared dx. In integrating, we have here a upper limit, which is 4, and a lower limit of 0. So it results into 1/16 x raised to 4 over 1/12 x cubed, which in result is equals to 3 feet. So it means that the centroid of the y bar of the shaded area of the parabolic spandrel is equals to 3 feet. Also, we have drawn a free body diagram to represent our object. So we can see it here. It has been proven that the center, the point of center of that shaded region is equal to the x squiggly line or y squiggly line. They are just equal when we're going to get its result the same to what the result of x squiggly line is equals to y squiggly line. We can call an object a composite area if an area is a composite of common shapes. Then its moment of inertia is equal to the algebraic sum of the moments of inertia of each its parts. Shall we now start solving our first problem on composite areas, where we are going to find the y bar and then calculate the moment of inertia about the x prime and the y prime. So the first thing we should do before solving is to draw a free body diagram, which will help you in better understanding or having this clear format of which variables to be considered or what values should be used or be inputted in a calculations rather. So in the object, we can observe that we have here this vertical and horizontal rectangles merged together, forming a letter T, somewhat letter T. So in our vertical rectangle, we have here a 20 millimeter height with a 150 millimeter distance. So we can easily draw or find out the centroid. So because the values are also exact. For example, this 20 millimeter height, we can easily say that the centroid locates on 10 millimeters. So on our horizontal rectangle part, we have here a height of 150 millimeters and also a 20 millimeter distance on the direction of the y prime. So we can easily also find its centroid due to its divisible value. So let us now begin finding the y bar of the object. So y bar is equals to the formula of summation of y squiggly line over a over the summation of a. So we're now going to add the product of the two areas of rectangle. So the first one is the first rectangle, which its center is 10 millimeters times its distance of 150 millimeters times its height of 20 millimeters. So the second part of the rectangle is we're having this 75 millimeters plus 20 millimeters times the total height of 150 millimeters times the 20 millimeters distance. It was just it was situated below. So the first rectangle is up and the second rectangle is down part. Over, so the product of the so the sum of that two quantity products will be divided into the two distance and height of the two rectangles, which is 150 times 20 plus 150 times 20, which in result 315,000 millimeter cube over or divided by 6,000 millimeters squared, which in result our y bar is equals to 52.5 millimeters. Now that we know where is the line that we are rotating, we can now calculate the moment of inertia. But take note, the moment of inertia of a rectangle about its center of mass is equal to bh cube over 12. So on our topic regarding with the parallel axis theorem, we're just going to use the same example. Since we have already identified the y bar, we can now somewhat like continue solving its parallel axis theorem. For the rotation about x-axis, we are going to need to use the parallel axis theorem since the x-axis doesn't pass through the centroid of either rectangles. So with the aid of our formula, which is ix, or the parallel to the x-axis, is equals to the summation of the I, or the moment, plus the area times the squared of the distance of y, which is equal to 20 millimeters times the 150 millimeter cube over 12 plus 20 millimeters times the 150 millimeters times the quantity of 52.5 millimeters minus 10 millimeters squared plus 150 millimeters times 20 millimeter cube over 12 plus 20 millimeters times 150 millimeters times the quantity of 95 minus 52.5 millimeters squared, which will give us the result of 16.6 times the 10 raised to 6 millimeters to the fourth power. So on the other rotation, which is on y-axis, we don't have to use the parallel access theorem since its y passes through the centroid of the rectangle we have. So the parallel to the y-axis is equals to the summation of our moment, where 20 millimeters times the 150 millimeter cube over 12 plus 150 millimeter times 20 millimeter cube over 12, which in result is equal to 5.725 times 10 raised to 6 millimeter to the fourth power. So this formula or this calculation are derived to the formula we have said earlier, which is base times height cube over 12. So that's our formula we used to base our result. So on our problem on the product of inertia, we have here a problem to which we have to determine the product of inertia of the shaded area with respect to the x and y axis, and then use the parallel axis theorem to find the product of inertia of the area with respect to the centroidal x-axis and y-axis. So we have here a base of 4 meters and a height of 2 meters with a certain point, or we can imagine later a certain region of the centroid of this quarter circle object, which represents y squared is equals to x. So as we can see, we have now put a dot or a point that will serve as our center of this shaded region or this shaded part of this parabolic, which our height is equals to y, and from the point down to the base is equals to y squiggly line is equals to y over 2, which will be used later, and our base is equals to dx. The area of the differential element parallel to the y-axis shown shaded, where our d area is equals to our y dx, which we have identified as x raised to 1/2 dx. The coordinates of the centroid is in this element are the x squiggly line is equals to our value of x, and the y bar is equals to the y over 2 or the 1/2 x raised to 1/2. Thus, the product of the inertia of this element with respect to the x and y axis is equal to the vi sub xy is equals to the vi bar x prime y prime plus the area of the bar x times bar y, which our d I bar sub x prime y prime is equals to 0. Then plus our d area, which is x is raised to 1/2 dx times our x bar, which is equal to the value of x, and our y bar, which is 1/2 of x raised to 1/2, which in result our d I sub xy is equals to 1/2 x squared dx. The product of the inertia performing this the product of this inertia, we can perform this through I sub xy is equals to the integral of the d I sub xy, which we have here an upper limit of 4 meters and a lower limit of 0, integrating 1/2 x squared dx, which in result to 1/6 x cubed, which gives us a 10.67 millimeter raised to 4 or 10.7 millimeter raised to 4. So we are now down with our last topic, which is about mass moment of inertia. We have here a problem which is a thin plate with a mass per unit area of 10 kilogram over meter squared. So our task is to determine its mass moment of inertia about the y-axis. But for easy solving, we can convert our units into meters. Okay, so the thin plate can be subdivided into two segments as shown in our free body diagram. Since our segments are labeled both holes, the y should be considered as our negative part. So the mass moment or the mass of segment 1 and 2 are as follows. So the mass of the segment 1 is equals to the 0.4 meters times 0.4 meters times 10 is equals to 1.6 kilogram. So we have get this value since we have a side of 0.4 by 0.4 meters times our mass, which is 10 kilograms. So which in result our mass in segment 1 is equals to 1.6 kilogram. So while in our mass of segment in 2 is equals to the pi times the 0.1 squared times 10, which in result will give us a 0.1 pi kilogram. The perpendicular distances measured from the center of each segment to the y-axis are indicated in our free body diagram. The mass moment of inertia of each segment about y-axis and the can be determined using our parallel axis theorem formula, which I sub y is equals to the summation of our I sub y times g, or our point g, plus our mass times distance squared. So which in result 2 times the quantity of 1 over 12, since we have identified before that in solving using a parallel theorem, we are always considering the constant of dividing 12 with the product. So 1 over 12 times 1.6 kilogram times our 0.4 meters squared plus 1.6 times our 0.2 squared minus to the quantity of 2 times 1/4 our mass segment 2 plus our 0.1 pi times 0.2 squared, which in result our mass moment inertia in about y-axis is equal to 0.144 kilogram times meter squared. So that's all for today's video. Goodbye and God bless.